All right, good afternoon, everyone. I'm Christian Clark, and I'll be presenting this work on recency bias in transformers. The work that we do here is grounded in surprisal theory, which I guess the presentation already brought up to some measure. But just to kind of reintroduce surprisal theory, the idea in this line of research is that a word's processing difficulty can be related to its predictability in context. Specifically, that difficulty is proportional to the negative log probability of the current word given the preceding linguistic context. This has become an influential area of research in computational psycholinguistics, in part because of the natural interface it creates between the task of psycholinguistic modeling and the task of language modeling, which is widely used for applications in computational linguistics. So some previous studies have compared surprisal measures from a range of language models used in computational linguistics to see how well they predict human reading times. So among these have been simple models like n-gram models, as well as more complex neural network-based architectures like recurrent neural networks or transformers. And these comparisons have generally shown a strong fit to human reading times from transformers. This latter result is interesting in part because of a clear similarity between the attention mechanism at the heart of the transformer neural network architecture and models of human memory based on cue-based retrieval. So I'll talk about this in more technical detail later, but just to give you some idea, if a transformer model is processing a sentence that starts out, "The dog chased its," at the word "its," the model compares a vector representation of its to vectors for all of the previous words in the sequence. And then based on the similarity scores from that comparison, it takes a weighted combination of information from these words, and that gets passed farther into the model and is used to predict next words. So in this aspect, transformers seem to have a lot in common with cue-based retrieval. But in some other ways, transformers don't line up as well with how we think human memory works. So one consideration here is that transformers condition their predictions of next words in a sequence on lossless representations of the previous words. Transformers also typically make use of a long context window or a text history, including a sequence of, or a history of ranging from a few hundred words in some older transformers up to even millions of words in the most recent models. And maybe the mismatch between transformers and humans is illustrated by some kinds of evaluation that have been done lately, such as the needle in a haystack task, where transformers fed a big long context of maybe a few 100,000 words with some specific piece of information embedded somewhere in the middle, and then asked to retrieve that information. And transformers show a decent ability to do this, which seems like a superhuman ability. So the fact that transformers work with memory this way seems to run contrary to how we think human memory works as it relates to sentence processing. So as a simple way of addressing this and trying to bring transformers more in line with how we think humans work, the work that I'll talk about tries adding a recency bias to transformers. This simply means that we shift some of the attention in the transformer to the most recent words. And this resembles ideas of decay or lossy context found in some other cognitive models. We test this idea by taking surprisal estimates from transformers with and without recency bias, and then using them to predict reading times in a set of broad coverage naturalistic corpora. And to foreshadow our results, we find improved predictions of reading times from transformers that include a particular form of recency bias called alibi. So in the remainder of this talk, I'll give a little more technical detail on how these transformers work and how recency bias is implemented. I'll then go over our regression experiments to reading times and end with a few discussion points. So I'm going to walk through some details about the transformer architecture here, which will admittedly get a little bit technical. I'll try not to get too deep into the weeds here, but my motivation is just to be able to precisely define how we add a recency bias to transformers. So a full transformer model can be described by a diagram like this that shows what happens to each word in the input. So a word passes through first, at the bottom of this figure, an embedding layer that turns the word into a vector representation. It's then passed through a sequence of transformer blocks in the orange here that manipulate this representation before some final transformations enable predictions of the next word. If we zoom into one of these transformer blocks, it consists of two main parts. The first is multi-head attention, then the second is a feed-forward layer. We're less concerned about the feed-forward network for this study. But if we zoom in even more to the multi-head attention, this diagram kind of shows how it's put together. The core component here is something called scaled dot product attention that I'll walk through a little more here. So the inputs to this transformer attention mechanism are word vector representations referred to as queries, keys, and values. And there's one of each of these for each word. When we're processing a particular word at index I, we proceed first by calculating the similarity between this word's query vector, qi, and the key vector for all the words leading up to the current word, kj. And this similarity is calculated as a scaled dot product, where the square root of d here uses the vector dimension d. We exponentiate and renormalize these similarity scores in order to get the final attention scores using a softmax representation, or softmax function that I represent as sigma here. Then these attention scores are used to take a weighted combination of the value vectors, and this weighted combination is then used downstream to help with next word predictions. One other important component of this model is the fact that multiple attention heads do this scaled dot product attention in parallel. So on the figure on the right, you'll see the H there kind of spanning multiple copies of this scaled dot product attention. That's because this is done multiple times in parallel within the model. It can be convenient to visualize the way that these attention scores are calculated using a heat map kind of representation, like I have on the right now. So here, each row of the heat map represents a query vector, and each column is a key vector. So let's say we're having the transformer process the sentence, the dog chased its tail. To process the word its, the query vector corresponding to its, Q4 in this example, is compared to all of the key vectors in the context leading up to the current word. So that's K1 through K4. Then the heat map shows with a darker color at dog that this word, for instance, receives a high attention score. So this is another way of visualizing what's going on in transformers that seems to have a lot in common with queue-based retrieval. The idea that we test here is adding a recency bias to these attention scores to upweight the most recent words. So if these are our raw attention scores, recency bias assigns a higher attention weight to more recent tokens in proportion to their distance from the current word. If we combine that with the raw attention scores, we end up with these modified attention scores that still tell us the original scores, but with this bias toward the most recent tokens. And in the experiments I'll talk about, we try two implementations of this recency bias from previous work. The first of these comes from a study by DeVarda and Morelli from 2024. Like us, they're interested in using modified versions of transformers to predict human reading times. Their approach is to add a recency bias term, BI here, to the similarity scores before renormalizing them with the sigma or softmax. The terms in this bias vector follow an exponential pattern based on the distance of the word we're attending to from the current word. And this hyperparameter lambda tells you the rate of decay. So this is their full attention formulation, where here on the right-hand side we have the original similarity scores between queries and keys. Then on the left-hand side we have the recency bias that's being added in. These are weighted using the hyperparameter alpha. And in our experiments, we use hyperparameters recommended in the original study. The other form of recency bias that we test is called alibi, short for attention with linear biases. And this actually came from some work in natural language processing that uses this as a method for input length extrapolation. But in a lot of ways, this is similar to the DeVarda bias, in that we add this recency bias term to the similarity scores. But here the recency bias follows a linear pattern, again based on the distance between the current token and what we're attending to. So that this is our modified attention formulation, again where we're taking this combination of the similarity scores and a recency bias. The hyperparameter m here determines the rate of decay in the alibi. And I'll talk a lot more about this later, but the original study uses a different decay rate for each attention head within a layer. Recall that I mentioned that a transformer block performs this attention process multiple times at once, and Presedal used a different decay rate for each of those. Having given that background, let's now talk about the regression experiments. In these experiments, we predicted reading times from a set of broad coverage psycholinguistic corpora. These included self-paced reading times from the Brown Natural Stories and UCL corpora, as well as eye tracking measures, also from UCL and then from Gecko, Dundee, and Provo in addition. The eye tracking corpora included a few different measures, scan path, first pass, and go past durations in particular. And we partition each corpus into fit, exploratory, and held out partitions, so that the fit partition contains half of the data points. We use this to fit the regression models. The exploratory partition, which has a quarter of the data points, is used for evaluation of the regression models. And then we reserve the held out partition, which has the remaining quarter of the data points, for statistical significance testing. The transformer models that we use to predict reading times are based on the Pythia model design. These contain a context window or a word history of 2048 tokens, where a token is, you can think of it as a piece of a word. And these are trained from scratch on the first 1,000 batches of the pile, which is a large English language internet corpus. So this works out to about 2 billion tokens. The models that we test have 2 transformer layers with 4 attention heads each for a total of approximately 27 million parameters. We chose both the parameter count and the amount of training data from an earlier study that compares reading time predictions from transformers that are trained on variable amounts of data and with varying capacities. If you're familiar with transformers, this 27 million parameters might look really small compared to some of the current models people use, but this small size was also helpful for us being able to train a wide range of transformers from scratch. Now to talk about the regression models, we predict reading times using a set of linear mixed effects regression models that include the predictors that I display here. Each regression model included a set of baseline predictors as well as surprisal-based predictors. For self-paced reading, the baseline predictors were the length of the word in characters, its index in the sentence, its unigram surprisal, and then eye tracking additionally included an indicator variable saying whether the previous word was fixated. On top of these, we have the target SERP, or surprisal predictor. We also include that spilled over from one previous word. The evaluation metric that we look at is the increase in log likelihood, or delta log like, which compares the fit of regression models with and without the surprisal predictors. And the delta log likelihood scores that I'll report are aggregated over all of the psycholinguistic corpora. Our first experiment is a replication of the DeVarda and Morelli study that introduced one of the forms of recency bias. So we follow their approach of training transformers with standard attention, so no recency bias, but then including the recency bias at inference time when we calculate surprisal. The gray bar here shows the improvement in log likelihood from a transformer surprisal predictor that doesn't include any recency bias. When we try adding these two kinds of recency bias, we don't actually do any better than this baseline. So that means that we don't actually replicate the improvement reported in this original study. One possible explanation for this is that there are some differences in experimental design. So we predict per subject reading times. The original study predicted average times. But it's also worth mentioning that DeVarda and Morelli see some variation in their results across the corpora they test. We see something similar here, although you can't see it in the aggregated results. So our results are maybe not so different from theirs. But our second experiment tries an alternative approach of including this recency bias during both inference and training, which follows the other study that I've cited, Press et al., that introduces alibi. So here, I'm again showing the results from experiment 1, this time with the baseline with no recency bias as a gray dashed line. So when we include the recency bias during training, but use the DeVarda and Morelli bias, we still don't improve upon the baseline. But as you might be able to guess from the way that I've scaled the y-axis here, we do a lot better with alibi included during inference and training. It improves the log likelihood by about 350 points, and we found that this improvement was significant from a paired permutation test. Now, one detail about alibi that I alluded to before is the fact that in its standard implementation, it uses different decay rates across attention heads. So the authors of the original alibi study give a formula for determining these decay rates that we've used thus far. So these are the rates that we use in the first two experiments. But this use of multiple decay rates at once seems kind of non-standard in the context of cognitive modeling, where a model like ACT-R from Lewis and Vasish uses just a single decay rate. So our third experiment looked at whether we could simplify alibi to use just a single decay rate to bring it more in line with these cognitive models. And these were the results. So the gray dashed line here is again the baseline with no recency bias. And to be thorough here, we tried some simplified models with just a single decay rate, but where we add the recency bias either at inference time only, that's the blue line, or during both training and inference, the orange line. In both cases, you can see we struggle to improve upon the baseline, though, which seems to indicate that this mixture of decay rates is doing something important. And that brings us to the fourth and final experiment I'll talk about, which is a more fine-grained analysis of the attention heads in a model with the original version of alibi with mixed decay rates. The hypothesis that we test here is that these different decay rates may be helpful for tracking different types of dependencies. So we look into this by testing the individual heads in a transformer with alibi for their sensitivity to three kinds of semantic dependencies. First argument dependencies, like the relationship between dog and bit, and the dog bit the man. Second argument dependencies, like between man and bitten here. And co-reference, like between dog and its, and the dog chased its tail. We identified instances of these three types of dependencies in the natural stories corpus using a set of existing annotations. And then we calculated a mean attention score for each dependency type that tells you how much at a given head word you tend to look at a dependent word within this type of dependency. And we performed this test separately for all the different attention heads in the model. So there are 8 heads in total with 4 heads per layer and 2 transformer layers. Now to look at the results. First argument and second argument dependencies follow a similar pattern here across attention heads, where we see the most attention paid to these dependencies in attention heads with high decay rates. So the decay rate of 1/4 is the kind of steepest decay that we try out in this model, and those attention heads tend to pay the most attention to arguments. For co-reference, we see a different pattern, where attention heads with a smaller slope pay more attention to the co-reference dependencies. And this is actually pretty intuitive because it may reflect the fact that these dependencies tend to span different distances. Co-reference tends to be a longer distance dependency, so it makes sense that an attention head with less decay would be able to look back farther and complete the dependency. So this seems to support our hypothesis that the mixture of decay rates in a transformer with alibi may be helpful for tracking different dependencies. So I'll now conclude with just a summary of our main findings as well as a couple discussion points. I started out by talking about a similarity that's been noted between transformers and models of queue-based retrieval. Despite this similarity, there are other ways that standard transformers seem to diverge from human memory. So as a rather simple way of trying to address that, we add a recency bias and find that this improves predictions of human reading times. But the improvement is sensitive to the way that we go about adding the recency bias. So we get an improvement in reading time predictions from alibi, but not from the de Varda and Morelli bias. And we also find that we don't get an improvement if we only add recency bias at inference time. Lastly, we find that a mixture of decay rates leads to improved reading time estimates, but uniform decay doesn't. This latter result seems particularly interesting, and it raises the question of how to interpret the mixed decay rates. So we see that these are indeed necessary for predicting human reading times, but they don't really line up with what we've seen in existing cognitive models like ACT-R. So a possible explanation that we explored in our experiment 4 was that these mixed decay rates may be helpful for tracking different kinds of dependencies that vary in how local they are. A related possibility is that the utility of using different decay rates may reflect the fact that these dependencies themselves may use different retrieval operations. And this is an idea that was independently suggested in a recent study by Yoshida et al. This is a little more speculative, but it even seems possible that this mixture of decay rates might actually track something more like interference as opposed to pure decay, by enabling attention heads to specialize to the features that have to do with specific dependencies and which might incur interference at different rates. But regardless of the correct explanation for the effects from these mixed decay rates, we hope that these results can be a starting point for more work in broad coverage modeling that draws connections between models of memory and expectation. So thank you all for your attention, and I'm happy to take any questions now.
Thank you. Lisa Levinson, University of Michigan. I have a question that I think it kind of gets into what you were getting into in the conclusions and discussion, but I wanted to make it a little bit more pointed or give you maybe some chance to follow up on it more. The question is essentially about what does this tell us about humans in a sense? So given that we know that humans have memory constraints, so it's like we know that there is maybe something like recency bias or these memory constraints in humans, what do you think we can learn about the human sentence processing, either from what you've done so far, or what are the next steps that's going to give us? You're talking about the modeling this and maybe these mixed decay rates, and I assume that the idea is that those models might interact with our other cognitive models, but I don't know, how close are transformer models generally to human cognitive models, and do you think at what point do those can really give us insight into human sentence processing?
That is always a good question with this kind of research. And I think I'd make a couple points in response to that, maybe a narrower point and a broader point. I think with regard to these particular results, I think it's an interesting finding that a transformer with a uniform decay doesn't predict reading times as well as a transformer with mixed decay rates. So you could take that, I guess, as a form of evidence against kind of a simplistic model of decay in humans. And I know there's some other evidence against that already and in favor of interference-based accounts. But that's one way that you could take these narrow results, I guess. The broader point I'd make is I think a lot of what I'm interested in these findings isn't so much, it's not some claim that a particular transformer-based model is a close match to how humans work, but it's more about the comparison between manipulated transformer models and what that kind of delta between the models might tell us about how humans work. It seems like if you see that adding a particular bias to a transformer model improves reading time predictions, that might motivate changes you'd make to a more directly cognitively inspired model. So yeah, I'm certainly interested in trying to continue to manipulate this bias to bring it more in line with how we think humans work. But I think just that gap between how different transformers perform can be meaningful for understanding humans.
Thank you.
Hi, thanks. Thanks for the talk. So I just want to open by, actually, it's relevant to your talk too, but pushing back on the first question from the previous talk. I don't see either that talk or this one fitting the label descriptive. A computational model, any model, is a way of expressing a hypothesis or a set of hypotheses, and a computationally implemented model is just one way of expressing a hypothesis that lets you test things in a particular way. So if you think in terms of MAR and the computational level, I see what you're doing and what in the previous talk was doing as squarely in the computational level of explanation and therefore explanatory. That said, it's kind of a follow-up to the previous question. I'm struggling a little bit with the boundaries between the hypotheses that you're trying to express in the cognitive space and the details of the transformer models, right? So you've got things relating to specific attention heads, for example, right? You've got aspects, and so I'm trying to understand where you're drawing the line, how you are teasing things apart so that you know that you're doing research on the cognitive processes. What aspects of the transformer models are and are not actually part of the claims that you're making, I think is a way of saying it.
That is a good question. Yeah, I definitely wouldn't want to subscribe to some claim that every detail of these transformer models is supposed to be meaningful. Again, I think, I think my best explanation is similar to what I was saying before, that the gap between these models if you're able to kind of make a similar adjustment to, an adjustment that's meaningful in the context of cognitive modeling for humans, it seems like talking about the effect of that adjustment is still going to be meaningful. I think also, if we're talking about adding decay in, we can try to make sure that the decay is similar to what sort of decay we would suppose would exist in humans. So that's another difference between the de Varda-Morelli bias and the alibi bias that I didn't get to here. The linear bias in alibi ends up translating to something that actually more resembles the exponential decay in a model like ACT-R, whereas the bias in the de Varda-Morelli model ends up being something really different. So I guess where you can, it seems helpful to try to make aspects line up. But yeah, that still is a good question. I don't think I have a full answer to it.
Great, thank you.
Hi, thank you for the talk. I think maybe just Grusha Prasad from Colgate University, kind of maybe following up on the Mars levels of analysis question. So I was wondering if you can say a little bit more about how you are thinking about this memory and decay, right? So at some level, are you thinking about this at a computational level? So specifically, I guess when you started motivating the recency bias, you said, oh, well, transformers have infinite memory, so then that's not ideal, right? But then you found that actually this uniform decay rate doesn't work, and your explanation was then maybe a more computational level account of maybe what is happening is tracking different dependencies. That seems to me like independent from a memory process, which at least intuitively to me feels like memory process applies consistently irrespective of the phenomenon, right? Like I have a memory that either decays or doesn't decay, and so it seems weird to say I have one memory process for one kind of dependency and another memory process for another kind of dependency. So I was wondering if you can elaborate on what level, so you're thinking about modeling this as like a computational level of this is what needs to happen, or are you thinking about this actually as telling us something about human memory and like saying part of what I'm doing here is modeling memory constraints and this is one way of modeling? Does that make sense as a question?
I think so. Yeah, I think with transformers, they do seem to, it seems to make the most sense to me to talk about them on a computational level of analysis where we're trying to impose, I guess where we're exploring different constraints that we could impose on transformers and seeing how that affects reading time estimates and kind of, not trying to get too deep into the weeds with all these details lining up with processes that we'd expect. But I think some of the long-term goal of this work is to try to take advantage of elements within transformer models that I guess seem to line up more with algorithmic models of comprehension. So yeah, I guess the goal is maybe to move from a more computational level model to an algorithmic level model.
Thank you.
Okay. Hi, Satvik Nair from University of Maryland. There's a great talk. I'll just keep my question short, referring specifically to how you're modeling effects on broad coverage comprehension. So I was wondering what sorts of predictions your modifications to the transformer model might make for these more constrained cases that we're testing, like syntactically complex sentences, whether they're like agreement, attraction, or garden path effects.
Yeah, I think that's actually very low-hanging fruit. I'm interested in testing a transformer that's been modified this way, but on some more targeted stimuli. I don't think there's really anything preventing that experiment from being run, so I think that would be a logical next step.
Right. I would want to ask more about what predictions it might make, but yeah, I guess we can follow up offline.
I mean, I guess it would be interesting to see if this was helpful for bringing surprisal more into, if it would be helpful for surprisal, for instance, capturing the full magnitude of garden path effects. That would be one thing you could test. Or I guess you might hypothesize that the recency bias increases the garden path effect. So that's one thing I would be interested in testing.
Thank you.
Okay, let's thank Christian again.